very best company in Pune, that is Serum Institute of India. I'm statistical advisor for this company, and I'm also teaching biostatistics in university at several departments, and I'm also using these biostatistics concepts in my research also. So I would like to share my experience, as well as I would like to share how these techniques are important in research, and specifically in pharmaceutical research. Hello.
So quality by design is systematic approach to pharmaceutical development that emphasizes designing quality into product from beginning rather than testing the quality only at the final product. So we design the product first and then we produce the product. So this is called as quality by design. So it uses the statistics to build the quality into products by identifying and controlling variability, focusing on critical process parameters, critical material attributes to ensure consistent and high quality outputs. So this concept was introduced by US FDA and supported by several guidelines like ICH guidelines. So these are few things which are very important to understand the basic biostatistics which I am going to cover in this section. So quality target product profile. It is a strategic framework used in pharmaceutical development to define the desired quality characteristics of the drug products. Critical material attributes. These are the properties of input materials such as API or excipient that must be controlled with appropriate limit to ensure the desired quality of the drug product. Critical quality attributes. These are specific physical, chemical or biological characteristics or properties that should be within the appropriate limit, range or distribution to ensure the desired product quality. And critical process parameters, these are the variables that can directly impact the product's critical quality attributes. So we have the input materials which are considered as the critical material attributes. Then we have the critical quality attributes, process parameters, and the output is critical quality attributes. So the design of experiments is a systematic or statistical methodology used in pharmaceutical industry to plan, conduct or analyze the experiments. So it replaces the traditional one factor at a time approach by varying the multiple factors simultaneously. So in traditional research, what we do is we vary one thing at a time, and then we check the effect, we see the response of that particular variable. But in this design of experiments or in this analysis, what we do is, and simultaneously we vary several parameters, and then we see the output, then we see the response. So it allows identify the significant interactions and obtain a design space. So in traditional approach, what happens is we could vary one factor at a time and see the response. We could not see the interactions which can happen between when the effect is there simultaneously. So design space is multi-dimensional combination and interaction of input variables like material attributes and process parameters that have been demonstrated to provide assurance of quality. So it is subject to regulatory assessment and approval. So my session is structured like this. First I will cover the very fundamentals of these three techniques, and then I will go towards the application part. That is, I will use some pharmaceutical examples to convey the better understanding of these techniques. So analysis of variance is the technique which is used to find out the differences between multiple groups. Okay, so in this case we see different factors, levels and response variables. So factors are independent variables, that is these variables we can manipulate or we can choose those variables. Whereas response variable is dependent variable, that is not decided by us, but that is decided by the independent variable. And there are several levels which are used, these are the specific values or groups within the factor. So suppose type of drug formulation is a factor, whereas tablet A, tablet B or tablet C, these are the labels. Like dose level is the factor, whereas 10 milligram, 20 milligram, 30 milligram, these are the labels. We can say that this has 3 labels. This is a factor with 3 labels. Like type of excipient use, that is lactose or crystalline cellulose. These are the labels. So we can say that this factor has 2 labels. In ANOVA we have the factors and labels, and by choosing these labels and factors, what we observe is a response. Okay, so this is measured output. This is the main variable of interest that you want to compare across different groups of conditions, and it must be measured on continuous scale or numerically. So remember, these are the factors which are categorical variables. Okay, so these are categorical variables, or you can say non-numerical variables, whereas response variable is numerical variable that we measure. And these factors are decided by us, but response variable is not decided by us. That is, it measured when these are the input variables. So like drug dissolution rate or blood glucose level after drug administration, drug concentration in plasma, total tablet hardness. These are some of the examples which are different from pharmaceutical evaluation. These are considered as the response variables. So you might have studied 1 way ANOVA and 2 way ANOVA. So before going to factorial ANOVA, I would just like to go through these 2 techniques. So in 1 way ANOVA, we study only single factor. Okay, so single factor may have multiple levels, and because of these multiple levels of single factor, they have multiple groups. So we have only one factor, and the purpose is determining if the group means are significantly different. Okay, so there are 3 or more levels of the same factor. So if we have only 2 levels, we can compare these 2 levels by using these simple techniques like p-test, student p-test. But if we have more than 2 levels, then we have to use ANOVA technique to compare these different levels, and then compare whether this output or variation in the data is same or statistically different or similar. And as name suggests, 2-way ANOVA is there are number of factors are 2. So there are 2 factors. Like in previous slide, I have given you examples of factors. Like if you consider only type of drug formulation, and if you compare only tablet A, B, C, then we use 1-way ANOVA. But at the same time, if you use the drug formulation as well as drug level also, dose level also. So tablet A with 3 dose levels, tablet B with 3 dose levels, and tablet C with 3 dose levels, then that type of study becomes 2-way ANOVA. Okay. And then if you understand this, then you will understand factorial ANOVA. Okay. So in factorial ANOVA, the factors are more than 2. So if you have multiple factors, more than 2 factors, then we say that it is a factorial ANOVA. Okay. So if there are 3 factors, then we say that it is 3-way ANOVA. But instead of using 3-way, 4-way, 5-way ANOVA, we use the single word, that is factorial ANOVA. So it is basically a 1-way ANOVA, 2-way ANOVA, and then factorial ANOVA. That is the hierarchy. So 1-way ANOVA example is, suppose we study the effect of tablet formulation on drug dissolution, and if you have 3 tablets, and these are the levels of each tablet, like 85. Sorry, these are the responses of these formulations. Formulation A, I have these 3, we have recorded 3 responses, and these are the 3 responses, dissolution rates. And then, and if you compare this with box plot, And then we can see that there are differences in this. So these differences, whether they are statistically significant or not. Okay. Differences doesn't mean that one is higher and one is lower. It should be statistically significant. That is, the p-value should be less than 0.05. If that is the alpha level or that is the significance level we are using. Sometimes we use significance level 0.01. Then if that is significance level, that p-value should be less than 0.1. So ANOVA checks whether the mean resolution percentage is significantly different among A, B and C formulation types. So that is very simple and straightforward statistical techniques. In two-way ANOVA, suppose we have the two factors. Factor 1 is dose and factor 2 is temperature, and we have measured we have decided the levels 10 milligram, 20 milligram, 30 milligram, and temperature 15, 25, 14. So it becomes 2:3 factorial design. 2:3 factorial design. That is, there are two factors and 3 levels of each factor. That means 2 into 2 into 2 into 3. So response variable is drug degradation, and if you compare this individually, then we check the main effects. Okay, so individual comparison will give you the main effect. However, we are more interested in the interaction effect. So what happens if there is interaction between dose and temperature? That is, particular concentration of drug at this particular temperature is more effective in dissolution, drug degradation or not. Okay, so if we are interested in that, then we see the interaction. So one way ANOVA there is no interaction effect because there is only one factor. But in two-way ANOVA we have the two factors and we can check the interaction. So you can imagine in factorial ANOVA if you have 5 factors, then how the interaction would be. So interaction between 1:1. That is, first factor, second factor, and third factor, first factor and third factor, first factor and fourth factor, and so on. So 1-to-1 interaction, as well as if there are 3 factors, 3 interaction at a time, and 4 interaction at a time, and 5 interaction at a time. So that becomes very complicated in factorial ANOVA. But to understand the factorial ANOVA, you should understand how this factorial ANOVA becomes complicated because we increase this factor. So here only 2 factors are used. But if you use multiple factors and see the response at a time, so these multiple factors, what these multiple factors have the effect on response. So that is what we check in factorial ANOVA. So it is the design where 2 or more factors are studied simultaneously and all combinations of factor levels are taken. So you can analyze the effect of 2 or more independent variables or factors on the single response variable. Response variable is, as I said, it is a dependent variable. So it also determines whether interactions occur between the factors. So the number of factors are more than 2, and the purpose is the main effects and interaction. So main effects of each factor as well as the interaction of these factors on the response variable. So this factorial designs can be written like this: 2x2 design, that is 2 factors with 2 levels. 2x3 design, that is 2 factors. First has the 2 levels, whereas second factor has the 3 levels. Or 3x3x3, that means there are 3 factors and each factor has 3 levels. Okay, so it becomes a factorial design. Okay, so it can be like this: 4x4x3, that means there is first factor having 4 levels, second factor having 3 levels, and third factor having 2 levels. So like this, you will have to multiply these things and then the product gives you the number of outputs. So here 3x3x3, that means in this case 3 into 2 is 6, whereas here 9 into 3, 27. So 27 interactions will be there in this factorial. So example is like suppose we have taken these 4 factors: dose with 2 levels, temperature with 2 levels, excipient type with 2 levels, and pH of the medium with 2 levels. Okay, so this becomes. So can you tell the product how will multiply? So it is already written. Okay, so it is 2 into 2 into 2 into 2 design. So that means it gives 16. So this factorial design has a 16 treatment, and response variable is only one, and it is measured on the continuous scale. So there are different scales of measurement in statistics. You might have a nominal scale, ordinal scale, ratio scale, or interval scale. So ratio scale or interval scale is considered as continuous scale. There is also discrete scale also, like number of students in this class. So there cannot be decimal point, 5 or 6. Okay, so whole number, when we get whole number of measurement, that is a discrete scale. When we get the values in decimal points, so that is considered as continuous, like height of the person. So it can be 160.23 centimeters, like that. So it becomes a continuous. So response variable is always measured on the continuous scale. So here main effects can be seen. So each factor individually, dose effect, temperature effect, excipient effect, and pH effect on what? On drug resolution. Okay. So how the dose is influencing the resolution rate, how the temperature is influencing, how the excipient type is influencing, okay, or how the pH of medium is influencing the drug resolution. Okay. So individually we can identify. So in traditional way, what we do is we vary one factor at a time. So we fix all these factors, like temperature is fixed, excipient is fixed, pH of the medium is fixed, only dose is varied, and then we check the effect on drug resolution. But in complex analysis or in advanced analysis, what we do is we vary these factors at a time, okay, and we make a design and we conduct the experiment simultaneously, and then on the basis of output we can decide which combination is best for this particular output. So when dose is 10 milligram, temperature is 40, excipient is B, and pH is 1.2, that combination is best or other. So you can make 16 such combinations. So out of these 16 combinations, which combination is best for given response variable, for given drug resolution? Are you getting my point? Okay, so we have a response variable, but we will have to find out which of these 4 factors, which combination, which level is good for, which is perfect, or which gives optimum yield of this particular response variable. Okay. So we can find out the interactions also, 2-factor interaction like dose and temperature interaction, dose and excipient, temperature and pH, or 3-factor interaction like dose, temperature and excipient interactions, and dose, excipient and pH interactions, and all factors together like dose, temperature, excipient and pH interactions. So all this information we get from the factorial. So this shows whether combined factors influence the response variable. So individually we can know, but combined together, how these factors influence the response variable. So such charts we get, like these are the outputs like AB, AC, AD. Okay, so we can designate these factors like ABCD, and then we can get these products. And ABCD finally we use the combined effect of all factors. So to get this data, we have a model, that is statistical model for factorial ANOVA, and the observed value is decomposed into meaningful components. So this Y is the output variable or response variable or dependent variable. So the value of this output variable depends on what? Depends on this overall mean, then effect of individual factors, okay, like factor A effect, then factor B effect, and so on, and then also interactions of factor A and B, and also there is a error term, which is the random error as in normal distribution. So all these factors influence the output variable, and this model, this is the statistical model for factorial ANOVA. So this model partitions or breaks the total variance which is observed in the response variable into the components attributable to the factors, their interactions, and the error term. So this is the typical ANOVA table we get in the factorial ANOVA. Like you might have seen the one-way ANOVA table. So there only we see the within source of variation within the groups or between the groups. Okay. So here what we get is source of variation in factor A, factor B, EV interactions, then error, residual, and total. So these are the degrees of freedom. Then sum of squares are calculated by some complex formulas, but nowadays statistical packages can be used to find out this. When I was doing my PhD, we used to use Excel, so we need to remember all these formulas and we have carry out all these calculations on paper, right? And then on the Excel sheet. But nowadays in statistical packages, just pull out the values and then we give out like this ANOVA table. Then we calculate the mean space by when sum of space are divided by degrees of freedom, we get mean space. And then finally we get the F values. Okay. So these are the F values which are considered as calculated F values. And there are critical F values. If you see the ANOVA table of the F value table, we have the 2 degrees of freedom 1 and degrees of freedom. So here are degrees of freedom, and then we find out whether this calculated value is greater than the critical value. So if this calculated value, this value is greater than critical value, then the p value becomes smaller than your alpha level, that is significance level. That is, if significance level is 0.5, then your, and if significance is this p value is less than 0.5, that means your calculated F value is greater than the calculated value, table value or critical value. Okay. And on the basis of this p value, you can say whether this factor A has effect on the response variable or not, factor B has effect on response variable or not, and so on. So here for simplicity I have only 2 factors, but you can check this for multiple factors, and we can check the interaction also. So whether there is interaction is there between the factors or not, we can check by using the p value. So if p value is less than 0.05, then only we can say there is an effect, there is an interaction. Otherwise we say that there are only individual effects, but there is no interaction. So interpretation, like here, for example, this is the study, the effect of drug dose and temperature. So two doses and 2 temperature, and response variable is drug dissolution, and these are the p values. So you can check here that those significantly affects the dissolution. That is, p value is 0.01. That means less than 0.05, and that's why we can say that this drug dose, that is 10 milligram and 20 milligram, will give different responses. Sorry, 10 milligram and 20 milligram will give different responses for drug dissolution. Temperature also has an effect on drug dissolution because p value is significant, and there is interaction as well. So it is marginal, it is slightly less than 0.05, but in statistics, if it is 0.05 or less than that, we consider it as a significant difference, and that's why there is an interaction also. That means dose and temperature individually, though they have effects, interactive effect is also present. So such interpretation can be drawn from the by using the ANOVA statistical method. So dose significantly affects the dissolution, temperature significantly affects the drug dissolution, and interaction also is significant. Like so I hope you understood about the ANOVA and factorial ANOVA, because if you understand that, then we will slightly go beyond this. So that is, next technique is multiple linear regression. So this technique is used for prediction of response variable. So in previous case, what we saw is what is the effect of these different variables on the response. But in this case, what we do is we have the already obtained data, and then we check, we predict the response. That means if you have the data for particular set of variables, then we can predict what will be the response, what will be the response variable value when the predictor variables are altered like this. जैसे मतलब if you see the TV channels and then if you see the weather predictions, तो इस साल बारिश कितनी आएगी और winds कहाँ जाएगी. Okay, so all these predictions are based on this regression analysis. So regression analysis is used for prediction. Okay, like इस साल गेहूं की फसल कितनी आएगी इंडिया में. So how scientists predict that? Okay, so on the basis of the already present data, and when this data is analyzed, then we get some particular model of this particular study, and on the basis of that model we can predict the future, or we can predict if these are the input variables what will be the output. Okay. So here purpose is prediction. We understand the relationship between the variables, we determine the influence of multiple factors. So example like predicting the drug dissolution rate using temperature, pH and concentration. So suppose you already have the data for a particular study, like different temperature, different pH and different concentration. Then we can predict if this will be the pH, if this will be the temperature, and if this will be the concentration of drug, then what will be the percentage of drug dissolution. That you can predict without doing the actual experiment. Because actual data is different, but if you put the different values, अगर आपने pH 5 और 6 पर काम किया है, but if you change it to pH 2 पर आपने कोई experiment नहीं किया, लेकिन you can predict what will be the response variable at this particular input variable. So therefore, multiple regression, linear regression is statistical techniques used to examine the relationship between one dependent variable and two or more independent variables. Okay, so output is only one, but inputs are multiple. Okay, so when there is only one output and one input, then we say that it is a simple linear regression. Okay, one x and one y. But if there are multiple x and single y, then we say that it is a multiple linear regression. So this is the mathematical model for this regression analysis. So y is the output variable or response variable, beta 0. So all these betas are considered as the regression coefficient. So beta 0 is the regression coefficient, special regression coefficient. We consider it as an intercept also. That means it is the value of y when all these given x's are zero value. So all these x having the 0 value, then what will be the value of y? So here also you can check. Like if x is 0, x1 is 0, x2 is 0, then these products become 0, because 0 multiplied with anything becomes 0, and then all these terms get cancelled, and then y becomes beta 0. That means beta 0 is the intercept, that means it is the value of y when all these x are 0. So beta 1, beta 2 and all these up to beta k, these are the regression coefficients. And x1, x2 and xk, these are the independent variables. And there is also error term in this regression model, because error term is given because the actual value and predicted value, there is a slight difference between them. Okay. So when actual value is subtracted predicted value is subtracted by actual value, then we get the error term. So the difference between actual value and predicted value, that difference is considered as an error. Okay. So smaller is the error, that means our model is more better. Our model is predicting the variables in a better way. Okay. So here goal is to estimate the coefficients beta to best predict the independent variable y. So multiple linear regression models the relationship between one dependent variable and multiple independent variables. And it extends the simple linear regression by incorporating several predicted variables simultaneously. So for doing simple linear regression, we use simple formulas like beta 1 is equal to summation of x y minus summation of x into summation of y divided by n and so on. But for this multiple linear regression analysis, we cannot do by simple formulas, because formulas can be one-page formula or two-page formula, and then we'll spend 1 or 2 days for calculating only one variable. Okay, so that is the complicated calculations. So best way is use the matrix for calculating this these regression coefficients. Okay. So here we use the design matrix, X matrix, where first column has only one value, second column is having first variable values, then second variable values, and so on. Okay, so these are all predictor variables. Then this is the response variable matrix, single. So generally matrix is denoted by rows into column. Okay, so it is n rows into one column. So n by one matrix it is, whereas it is n by n matrix. So we have the multiple rows and multiple columns also. And coefficient vector is also it is n by one matrix. So what we do is we find out this. We get the response vector, that is y matrix, by multiplying this x matrix, x design matrix, with coefficients beta matrix, and plus we add the error matrix. So that is the compact formula for this multiple regression analysis. But for doing calculations in Excel sheet or some other software, we use this type of design. Like this is the vector, beta vector, that is these are the regression coefficients. We get the matrix of regression coefficients by doing XT, that is X transpose, that is matrix X is transpose. Okay. Then it is multiplied with the X matrix. Transpose is simply columns are converted to rows and rows to columns. And then take the inverse of this product, that is inverse of HTX matrix, and then multiply with HTY, that is X transpose multiplied with Y matrix, and then this complicated calculations will give you the variables. So this formula generalizes the simple linear regression to partial theory. So here, I hope it is visible. So this is the data collected on the simple random sample of 20 patients with hypertension. The variables are, the Y variable is mean arterial blood pressure. So blood pressure of 20 patients is measured, and we have to find out whether the blood pressure is dependent on age, that is the first predictor variable. Then weight, body surface area, duration of hypertension, then pulse rate, and the measure of stress. So whether this arterial blood pressure is affected by any of these or not, we have to find out. Okay, so that is the prediction we are going to do. So data is like this. There are 20 patients. Then these are the output. Okay, so these are the blood pressure values, and these are the age values of patients. These are the weight of the patients. These are the body surface areas. These are the duration of hypertension. These are the pulse rates, and these are the stress levels, which are measured, and then data is put into such matrix. Okay. Then how we calculate this? Okay, so I will show you the Excel file where these calculations, these complex calculations are done. have designed this matrix. So this is N111 and then X1, X2. We have the 6 input variables and 1 output variable, and then by using the matrix calculation. So this is XT, X transpose, XT, and this is X. Here, this is X, this is X transpose, and this is the product of XT into X. So we get another matrix. This is called as XT, XTX, and then we